So thanks, Paul, and thanks everybody from StarRocks team for inviting me, and thanks to the audience. Very happy to be here. I am going to be talking today about StarRocks and how we use it at Celonis. Celonis is a process mining company. So let's get started. So I'll give a brief introduction of what we do. So basically, we're a market leader in process mining. And process mining is a technique to discover processes in companies and to analyze inefficiencies, why the process is not working, suggest optimizations. For example, if maybe there is a process where you pay an invoice twice, so they will automatically detect that and make suggestions to improve it. With regard to the data side of our company, we basically have like three components. We extract data from customers, we apply some transformations on ETL, and then we do analysis. And the analysis part is what we do using StarRocks. Before I get too deep into how we use StarRocks, I have to talk a little bit about PQL. This is an internal process query language that was created by Celonis. And the main idea is that this is a domain-specific language that is tailored to do process analytics in an efficient way. There are some features of this language that are interesting. So if we compare it with SQL, SQL is mostly computing tables. Every query, every subquery produces a table. In PQL, most of the computation produces a column. And there is some advantages of producing columns. And that comes to the next point, that is the composability. So a user can define a KPI, a performance indicator, and it's just a formula, like column 1 plus column 7 minus column 13. And these columns can come from different tables, and the language automatically joins the different tables and computes this KPI. And this KPI can be embedded in any other formula. This is different from SQL, where composing two SQL statements is quite non-trivial. The other aspect of PQL that is interesting is that it's dashboard friendly. A lot of the surface of analysis is a dashboard. And it is dashboard friendly in multiple ways. One is that you can create filters, and these filters apply automatically to many queries in the dashboard. So you can have a table, you can have a pie chart, you can have a bar chart, and you add a bunch of filters, and these filters automatically are propagated to each of the elements in the dashboard. And the reason that we can propagate these filters automatically is because we have this concept of implicit joins, and we can join the tables in the filter to the tables in the query automatically. And basically, if the rows join, it means that you pass the filter. If they don't join, it means that you don't pass the filter. And of course, it has process operators. So operators that are specifically tailored to process analysis. Some of them are like, for example, match process. So you give me a sequence of events, and then you ask me, does this sequence of events match a certain process definition? And we can say yes or no. Or we can take all the events that happen in aggregate, and we can test if the history of all the events match a certain process definition. We can also create event logs. This will become a little bit more clear in the next slides. We can compute statistics about processes. We can do clustering. So a lot of algorithms around processes. Okay, what is the data that we work on? So basically, it's just two things: objects and events. Objects are just entities, like a purchase order item, delivery. That's just an object. And then we have events. And events are basically actions that happen to an object. We have relationships too, that is like end-to-end joins between objects and event tables. The event log is a central concept of Celonis, the central concept in our data. And this is a very simple idea. Is basically an ordered list of events that happen to an object. So an example can be, say that you have a purchase order, and then at T1 you create the order, at T2 you add some item to the order, maybe you add another item, then you remove an item, then you close the order, maybe you deliver the order. So just the events that happen to this order object. And there is some process modeling, as I said before. So basically, we need to derive some representations of your process. This usually looks like a finite automaton, like a Petri net. There are different ways to represent the process. And we take the data model and we construct a physical representation. And the physical representation are just going to be objects, events, and relationships become just tables in StarRocks. And these tables form a cyclical join graph. Now, why did we choose StarRocks? So it's a state-of-the-art cloud-ready query engine, and we in our team, a lot of the members of the team, our lead is Jeff Norton, who is a pretty well-known database researcher, and has worked on this area for many years. And many of us come from building query engines at Google and other companies. So we know very well how hard it is to build a good query engine. So we looked at StarRocks and we thought that it had the right structure. We like it. So it's much better to extend the StarRocks than to start from scratch. There are some specific features. We like the license. Apache license is very friendly, so we like that. The performance is pretty good. The execution engine is good. The optimizer is very strong. It's scalable. We can add nodes. We can remove nodes. It's extensible. This is important. I'll talk much more about this. So basically, we can take the source code and we can add new native functions. We can add analytic functions. We can add scalar functions. We can change the optimizer. And this is very important because out of the box, StarRocks is not going to do all the things that we needed to do for process analysis. And it integrates well with the open source data ecosystem. And I think a lot of the talks that we have seen today, people are integrating with Postgres and Iceberg, and they're reading data from other data lakes. So this is important to us. There are some challenges for our team in order to use StarRocks for process analysis. And basically, we need to teach StarRocks how to do it. We need to write all the functions to do it, and we have to do it at good performance. Remember that a lot of the analysis is done through dashboards, so we want to have most of the queries and produce a result within 2 seconds, maybe within 10 seconds, but we cannot wait minutes for these queries to be answered. I'll now go through some of the areas of StarRocks that are important to us and why. The first thing is the cost-based optimizer is pretty important. And this is because PQL is this interesting language that can produce very complex queries. So in PQL, we can have queries that can easily join 10 tables in a single query. This is because in PQL, you don't need to specify any of the joins. So you just define a query that is going to list a set of columns that you care about from different tables. We find the join path between the tables that appear in your query, and then we need to join all the tables in order to resolve the query. So the number of joins is high. We looked at different alternatives, and we found that even though they are very fast at working on the normalized data, when you have these queries that have 10 joins, they don't work well at all. And we don't have the opportunity to denormalize. It would be too expensive. So we found that StarRocks has very good performance with complex queries with many joins. Also, the optimizer has this modular design that is easy to extend. For example, it has been extended to handle cardinality estimation for arrays. We have extended the cost. We have extended the logic to estimate, to add different estimators for cardinalities of columns in tables, and improve some strategies for skew joins. So it's easy to reason about, and it's easy to extend. Continuing on the optimizer, statistics collections are very important. For us, having bad statistics almost certainly means that the queries are performing poorly, because our databases are usually large, like in the 5 billion range, 5 billion on the smaller side, and up to, I don't know, 20 or 30 billion sizes. And if you're executing 10 joins on tables of that size and the statistics are incorrect, the query is not going to work well. And we have the ability here to do full table statistics, compute sample-based statistics that are updated frequently, and maybe most importantly, we can compute statistics on individual columns. We can compute histograms on individual columns, and we do this for foreign keys. So when we do joins, if there is a skew, we can the optimizer can catch this information through the column-based histograms. And I said before that in PQL, the propagation of filters to the queries, to the widgets, that each widget is defined by a query in a dashboard, is very important. So applying filters efficiently is very important. And what I mean by applying filters efficiently is that when you process a query, you would like the amount of resources that are required to answer this query to be proportional to the number of output rows that match the filter, not proportional to the total size of the table. So this is pretty important to us. We find that there is very good predicate push down to scan nodes, and because we push down the predicates to the scan node, we are able to skip reading a lot of the data that doesn't match the filter. And even more important than that, we are able to push down filters across joins, and this allows us to really reduce the data size that needs to be shuffled for the join. And there is this nice feature about runtime filters that these are filters that are computed at runtime as you're evaluating a join, and you can significantly reduce the size of one side of the join if the other side has a selective predicate. And joins. So there is a good collection of join strategies in the StarRocks. Shuffle join is like the default. If nothing else works, we can always do shuffle join. But we prefer to do broadcast join whenever possible. Broadcast join is helpful, for example, in doing dimension to fact table joins if the dimension table is not too large. And the main advantage of this broadcast join is that it's very robust to skew. Shuffle join is not robust to skew, but broadcast is. And the most powerful join type that we have is collocated joins. I'll talk a little bit more about this in the next slide. But basically, collocated joins allow us to very efficiently co-partition the tables and execute the query on these co-partition tables. Join reordering, I talked already about that. It works well. We are surprised that we have some queries that have 50 joins and the join order seems to be mostly correct. And the evaluation of joins is quite efficient. On collocated joins, basically we have this data model. The data model is a bunch of object and event tables, and we know the joins. So what we run is an algorithm that tries to partition the graph into components that can be collocated. Basically components that have join keys that share some column. Maybe order ID is present in multiple tables, and then we partition all those tables by order ID. And this join is very, very efficient because it scales linearly. If you can, there's no shuffle, there's no communication among the different nodes. So if you have 20 nodes, it's twice as fast as if you have 10 nodes, and it works very well. We try to use it as much as possible. Okay, for aggregation, I think every single PQL query involves aggregation. It is really important to us. And StarRocks is very good at aggregation. And I want to speak about a particular strategy for aggregation that is sorted streaming aggregation. We use this especially when we're creating the event log. So basically the event log, as I said before, is that for every object, we have an array, we have a list of the events that happen to that object. And if we have the input data sorted correctly by object ID and maybe event timestamp, Then we can use sorted streaming aggregation, which is not blocking. As the name says, it's streaming. It minimizes the memory because we only need to keep in memory like one group, and it's pretty efficient. So this works well for us. There is this feature in the StarRocks that is called a query cache, and this is basically a mechanism to cache the leaf side of an aggregation. And for us, it doesn't work so well. We continue to look into this area, but it's not as useful. In terms of modeling the data for process mining, I think there are a few features that are quite important to us. One is strong array support. We use arrays to model sequences of events, and the basic idea is that we want to execute the queries mostly in array space. That means we don't want to unnest the arrays. We want to stay in the array space as long as we can. And the basic idea is, like, for example, if you have a filter, you use array filter. If you have some expression on the array, you have array map. If you want to do an aggregation on the array, you have array ag. And try to map the queries to these array operations, which are much more efficient than having to unnest and then maybe renest the data. And the other feature for data is that complex data types are important. A lot of the process mining algorithms produce complex results, multidimensional types, and what we use is mostly JSON, and the support for JSON in StarRocks is pretty good. So many of our native functions produce JSON as output, and some of them consume JSON as input, and this makes it easier to extend the engine without having to use just a collection of primitive data types. Okay, so now in terms of the right side, I've been talking a lot about the modeling, the optimizer, joins, and the query side, but now updates are important to us. One of the main reasons that we are working on building the query engine on top of StarRocks is that it allows us to update the data almost in real time. We don't have to do a lot of pre-processing. So it's an important feature because customers want to be able to do analysis very quickly on their data without having to go through a very heavy ETL phase. And there is one specific feature that is important to us, and this is partial column updates. And partial column updates is a mechanism that StarRocks, I think, developed specifically for Celonis. The idea is that we can update a subset of columns in a table in time and cost that is proportional to the set of columns that we're updating, and not in cost that is proportional to the entire data. Resource isolation works well. We have these clusters. We have many tenants in the same cluster, and we use resource groups to handle the isolation. We can isolate memory, CPU, and parallelism. I/O, it's a little bit more tricky, but we're working on that. And there's this new idea of multi-warehouse where we can actually separate a set of workers devoted to certain workloads. We are experimenting with that, and it looks promising. As I said before, StarRocks is very extensible. We have added hundreds of custom native functions, including scalar functions, aggregate functions, table functions, analytic functions. And the framework is clean, it's easy to add, it's easy to test, to benchmark, to check correctness. So extending the engine is a very important feature for us, and it works well. As I said before, it integrates very well with the data ecosystem, change data capture for tailing logs from Postgres. There's a Kubernetes operator that works very well. It's very easy to deploy to cloud. We can read data from Iceberg. We can write data to Iceberg. So these features are interesting to us. Maybe quickly, some areas of improvement. And I think there is already work on this direction. One of them is query evaluation in dictified space. So a lot of the data in business applications, like from SAP, are strings. These systems love strings, so many columns have the type is a string, and the characteristics is that the number of distinct strings is not too large. There is only a few thousand distinct strings. And if you are able to evaluate the query on dictified space, it's very, very beneficial because you never need to expand these two strings. And I think there is work in StarRocks in this direction, but it needs to be the coverage needs to be increased to, for example, handle analytic functions in dictified space. Sorting is a little bit of a problem. We do a lot of sorting, and sorting is a single node operation in StarRocks. We need distributed sorting to improve some of our workloads. And finally, high QPS of small updates has some bottlenecks. We get around it by doing some batching, but FE has very coarse locking, and sometimes this can get in the way of high QPS. Results, I think we are pretty happy. We have data models with 20 billion rows or more, and the P90 is around 20 seconds. We can do pretty fast data ingestion, very fresh data, and we can tune the system. We want more fresh data or we want more performance. So if we want more performance, we can do more pre-processing. If we want more freshing, we can reduce the pre-processing, and we can produce queries faster. So I think overall it works pretty well. Thank you. I think we can
Great.
go to questions.
Thank you so much, Hector. That was awesome. We have a minute left, but I think we have a little bit of wiggle room because there is a break built in right after this. So let's get to a couple of questions that have come in. They're starting to really roll in here. So are you planning to use the flat JSON new feature in StarRocks?
We have not looked into this yet. We will need to evaluate it.
Gotcha. Have you tried converting any of your JSON to fields or tables and compared read performance at your scale?
So this is a good question. A lot of our JSON is the result of an aggregation. So the number of JSON objects that we produce is small. Many times, for example, if you want to compute a model for a process, then we will produce a single JSON object that defines the entire process. So we don't do JSON operations on billions of rows. It's usually a few thousand JSON results. So it's not as important to us, the performance of the JSON compared to native columns, scalar columns.
Great. I think we are at time. So thank you so much, Hector. That was fantastic presentation. Don't forget to complete the evaluation question, which is in the polls right over here already.